Hello everyone, welcome once again to MOG Economics YouTube channel. In today's class, we are going to be looking at another interesting topic, which is difference equations. So now, for the sake of this class, we are only going to be considering the first order difference equation. The first order, and what do we mean by the? Okay, let's start with the definition of a difference equation. What do we mean by a difference equation? A difference equation expresses a relationship between a dependent variable and independent variable or variables and the lagged value of such independent variables or variables, as the case may be, depending on the number of variables that we have in a given function. So what a difference equation shows basically is expressing the dependent variable as a function of the lagged values of the independent variables. Alright, but in this case, for the case of this class, we are going to be limiting this class to the case of first order difference equation. Now, the order of difference now, at this point, we are interested in knowing the order of difference. What do you mean by the order of difference? The order of difference basically is talking about the greatest number of lagged value that we can have in a given equation. The greatest number of lagged value. So in the case of the first order difference equation, it means the dependent variable now is being expressed as a function of the 1 year or 1 period lagged independent variable. Yes, it's a 1 period. You are expressing the dependent variable as a 1 period lagged value of the independent variable. Alright, so in this case, let's assume we have this function which expresses investment at a particular period, which is period t here, a particular time period, which is not clearly stated, but we are talking about a particular time period. So the investment at a particular time here is a function expressed as a function of a 1 period lagged value of the income level, which is y in this case. So a 1 period lagged value. So and here um, it's important to know that when we have when we express this across time, when we measure the change in y to change at a particular period of time, or when we say we have something like this, what we basically mean is we are saying this in the current period and this just like this. Like this is the income level at a particular time period, that is at the current period, and this is the income level in a period's time, yeah, or in the future time. So this is what we basically mean by, and this stands for the rate of change. So which also means this can also be expressed as in this case can also be expressed as e with time. That is, you are expressing the change in this across time. So it measures the rate of change. So where this delta sign stands for the rate of changing in the income level across time. So here we are moving from the current period to the future period. That's what we have here. Now, at this point, we need to understand the different forms in which um, different equations can be expressed. Now, here we have different equations of different orders. Now, for the first case here, this is a difference equation of order. Now, before we even look at this, we need to understand that um, this particular concept we are dealing with is a dynamic concept. And what do we mean by something being dynamic? It means we are trying to understand economic relationship not being static, but economic relationship that are expressing themselves over time or that are moving over time. That's the meaning of dynamic, and that's what makes it different from static. You say something is instantaneous, like it happens just at once. But one thing we need to understand is that most economic relationships are dynamic, and that's why this particular concept um, um, really finds, and that's where this particular concept really finds its application, because most economic relationships are dynamic. So most times you understand that one variable relates to another variable not instantaneously but across time. Like the current consumption will not only depend on current income but also past level of income. So just like that. So and it is in that area that this particular concept really finds its relevance. So now, like I said, we have different orders here of differentiation of difference equation being expressed. Now for this first one, it is the order two. That's like I said earlier, I said the order of the difference equation now talks about the greatest number of the lagged value of the independent variable. Now in this case, the greatest lagged value here is period 2. This second one, which is t minus 2. That is the greatest lagged value that we have in this equation. So we have investment being expressed not only as a function of a single period lag value but two periods. We are saying, okay, investment is now a function of income level that's in two periods ago, something like that. Now, the next one here is a very familiar equation which we know. This is supply function. Here, supply is being expressed as a function of price. Now, the quantity supplied at the current period now is a function of a one past period or a one period in the past, if there's anything like that. So, and the greatest number of order in this case is just one because it's lagged by just a single period. So this is it, p t minus 1. And for this third case, the highest order in this difference equation is 3. The highest order here is 3. So there's something I would like us to understand at this point. If we have something like this, if we have y plus 1, and let's say it's being expressed as a function of, let's say, another income level, which is this. Now, what this says is the income level in the future time, that's in one period's time, will be a function of income at the current time. Now, this can also be expressed alternatively as this. Now, if we lag this particular function here, or equation here rather, if we lag it by one period, like deducting one from the period, number of periods we have. So here we're going to have something like this. Then here this cancels this out, and then here we have this. Now, what happens here is that we are only lagging this two period by one, which is still the same as this. So in case you see this, an alternative way to express this is to have something like this. To say, okay, what this one is saying is that the income level in the current period at the moment is a function of the 1 year period, past period income level. So that is, they are basically saying the same thing. It's just that here we are moving back by one period. We are going back by one period. And this one is moving forward by one period. So they are basically saying the same thing. I just think I have to clarify that before we proceed. So now this here, so in case you are saying plus plus, when we lag by one period, it's just like we are moving back and forth in time. That's basically what we are doing. Lagging by one period and adding a period to it is just moving back and forth. So they are basically saying the same thing. So here, the greatest order of difference of our different in this difference equation is 3. So that's order 3. That means this difference equation is of order 3. And if we look at this here, this is of order 1, which we can further express as from what we have here. This sound is delta yt. We can further express it as this, which is equal to, now we have something like this. If this is taken to the other side here, we have yt plus 5yt, which is 6yt. Now this has been simplified, and here we can clearly see that this is a difference equation of order 1, because the greatest number of order we have there is just 1. So by simplification we can see that. Now very quickly we are going to look at the iterative method of substitution. Like we difference equation, actually there's a general formula, just like we have done in previous classes where we came up with formulas for Maclaurin and Taylor series of expanding function. Now this difference equation as well also has its own formula, which is like a general formula. But coming up with this, there's an iterative method of actually arriving at this formula. But this formula just takes us directly to solving the question. But this iterative method takes us through the process of actually getting to that general formula. So here, by substitution, we do a successive substitution, or what we call recursive substitution. So here, we substitute for the first time period here, which is 0. We substitute it here, we have this equals 1. So here, basically what we are saying is y1 is function of this. So now, moving by one period again, we have 1, that is substituting 1 again into this. We have here becomes y2, and then this becomes y1. Now from here we already have our y1 to be this. So by recursive substitution, substituting this, the result for our y1 here into this, we have which is then, so our y2 is then so again, if we consider the second period and then we substitute again into this equation, we have now it becomes 3 substituting, and then this becomes b y2, sorry, b y2. But because in this case we already have a result for by2, y subscript 2 to be this, so we just simply substitute, then we have which again is and then we'll continue like that. So if we continue by recursive substitution, we'll continue, and then until we get to, we then have the unknown time period now, which is, let's say, the highest number of points or the highest point which in the future we can get to, which will then be, because now if you notice this series, the way it proceeds, you notice that okay, from the power of 1 here, this increases to 2. Notice the power of b here, it keeps increasing, then here to 3, 4, then successively like that. So at period t, and this is t, which is a period in the future that is unknown now, then this, and so the series continues in that pattern. Now okay, also another quick way to recall this process is looking at this. For the first period y1, the power increased to 1, then by looking at the second period, the power of b increases to 2, and then the third period power increases to 3, and then continuously like that till you get to t, and then this is that period in the future that is unknown, which is the last period. And now um, so now let's move on to the general formula for first order linear difference equation. Now at this point, I don't want us to really bother about the proof of this, but the thing is you just have to know this formula by heart. You know the formula, you have to know this formula, which is the general formula for first order linear difference equation. So if you are given a function, this is a function like this, where this is the first order difference equation, because the highest order of difference here is just 1. So yt is expressed as a function of itself, just one period in the past. So now the general formula here is just this: yt equals y naught minus a over 1 minus b, and b used to the power of t plus. Now when now there's a caveat, let me say, to this. So when b is not equal to 1, this formula will be applied. This formula, which we are going to see in most cases, this formula will be applied. But when b is exactly 1, work with this. I hope you get that. So now, at this point, I would like us to consider a particular example. So, all right. So let us consider an example at this point. So here we are applying the general formula we have just seen here to solve this. So now here, most of the time, in most cases rather, you'll be given an initial value. You'll be given. So in this case, the initial value, which is the y naught here, is 5, and then also you'll be given the value for b. B is -7 and a is okay. All right. So by applying the formula, we have our general formula to this. So let's recall our general formula. Okay. Then b always power t plus 1. All right. But one thing we'll notice in this case is that our b, now this, we can apply this formula here and not this, because in this case our b, the value for b here is not equal to 1. In this case is -7. Our b from this equation, so this just follows this normal equation we have here. So here in this case, this is the b, so it is -7, and a here is 16. So since here our b is not equal to 1, this formula can be applied. So, and from the values we are given here, just all we just need to do is to substitute. So here we have this to be, the initial value here is 5, then a is 16, sorry, from here, and then we have -7 as b, here a is 16, and then 1 minus 7. All right, so here let's just simplify this. Here we have 5 minus 16 over 8. This is 1, this becomes plus, and -7 to the power of t plus 16 over, this is 1 plus 7, and that is 8. So from there we have, that is, we have 5. So 16 divided by 8 is 2. We have 5 minus 2. So 16 divided by 8 is 2. So here we have yt equals 3 minus 7 is power of t plus 2. So now this is the answer. And then now this equation can be evaluated at any time period. So because if you are asked to evaluate this at, let's say, at period 2, all you just basically have to do is to substitute to have 2 here. At the second period you have this, and then 2 plus. So then this becomes 49, then times this, you have the result. That's if you are told to evaluate this particular equation at any time period. That's when you do that. So at this point, I said, like we were saying the other time, if we decide to evaluate this equation at time period 2, this is the result. So you might have to evaluate this equation at any time period. So now, at this point, we are going to be moving into another subtopic under this, which is stability condition. So it's a condition to know whether or not the function is stable. So in this case, let's have this our general formula has been written as this. This is y subscript t equals a b. Now here we have represented, going back to our general formula, this is general formula here. This here and these two entities here, we have represented them with different letters just to simplify the whole thing. Now here, A stands for this, the first bracket, first entity, those entities in the first bracket, and for the C, the other part, which is this. So now, this first part of this function here is regarded to as a complementary function, or what we can see as the deviation from equilibrium. Now the idea of stability condition is to check whether or not whether if there is a deviation to the equilibrium state, whether that equilibrium will be restored again. Like that's basically what stability is talking about. Like we want to see if maybe there's an external shock or a change in the policy environment or anything that causes a shift from equilibrium. We want to see if that state will be restored after some time, whether the thing will find itself back to equilibrium. And that's what we are basically doing when we are talking about stability condition. So now, like I said, this first part of the function here is a complementary function, which is talking about the deviation from that equilibrium. Now, the particular solution here is the intertemporal equilibrium, also known as the intertemporal, which is C here, which is the particular solution. So here we say this particular function here is stable only if this approaches zero. That's this. If only this approaches zero as we move in time periods, as we move from one time period to the other, that is, as this tends to infinity, as we continue like that towards the future. If this approaches zero, then we can say that the function is stable. The particular function we are considering is stable. Now again, this depends on the value of b, the base here, and that is why we can have different time parts being generated solely depending on the changes in this base here. All right, so at this point, like we said the time parts with varying values of b. Now the time part now will depend on the specific value assumed by the b in this case from this. So the value of b here will determine the time part of the function, or how the function will be graphed. Now, looking at this, we need to understand how each of these components of this equation affects the way the function will be graphed. Now, here we have established that this is a complementary function, which is the deviation from the equilibrium. This is the particular solution, which is the intertemporal equilibrium. So now, when this, looking at, let's start with the first term here with the a, letter a here. If it assumes a value different from 1, it could be, let's say 2, 3, or any value different from 1. Now what that will do is to scale this up. It will scale this b raised to the power of t up by whatever amount it assumes. So if it is 2, that means this will be scaled up by 2. If it is 3, this will be scaled up by 3. So if a is not 1, the value of the multiplicative constant here, this is the multiplicative constant. This is what we are referring to here. That is this b raised to the power of t here. We assume different value depending on this. So if it is 3, this will be scaled up by 3. If it is 4, this will be scaled up by 4. So but now the thing is the pattern of movement will still stay the same, but it's just that this will only scale this up. It's just like we talking having something like shift. It's more or less like having something like shifting the curve, but that same pattern will still be maintained. Um, all right, and for a situation where this is uh, this is one, when a so in a situation whereby this a is one, what happens at that point is we only have a mirror image, yeah, of the time path. So um, the time is just a mirror image. It's not affected. The pattern of movement still stays the same. Still stays the same. So we only have a mirror image in that case. And now for this C here, this one changes the intercept. This is like more or less like the intercept here. This is like, if you look at, if we compare this to a normal linear equation, like a simple linear equation, where we have a, let's say, x plus c, something like this one. Let's write it this way. The situation, this is a simple linear equation. So something like this. This here is just more or less like the slope, and this one is the intercept in this case. So this one will only cause a shift to change the intercept in this case. So now that we are familiar with each of the terms in this function, so now at this point I would like us to consider different cases of this value there, of this b assuming different values. We have different graph depicting or showing the different value assumed by this b from here. So in a situation whereby b is greater than 1, what happens is we have explosive time path. What do you mean by explosive time path? That is the you always have a dispersion away from the equilibrium, from that equilibrium state. We have the equilibrium not returning back to the starting point. It will keep diverging and diverging away from that state. So in this case, where in a situation whereby here we can see here that b is greater than 1, and here we have like a form of step. That is why we form of step. It's which keeps increasing. Now notice here it keeps increasing at an increasing rate and then continues like that, always moving away and away from the equilibrium state. Now for the situation where this value is 1, this is this stays the same, it remains the same, it is flat all through, so across time period. Now in this case we are we have our time period on the horizontal axis, and then this b raised to the power of t on the vertical axis. So since it is constant, it is flat all through, so across time stays the same at that particular value 1, stays the same. So for this other one, in a situation whereby the b value now is between 1 and 0, that is it's greater than 0 now but less than 1, if you have the time path across time, what happens, it keeps, you know, decreasing, and at the same time moving away from the equilibrium state, from that particular state, which is the intertemporal equilibrium. You have a divergence away and away, but in this case it is decreasing. Now for the next one here is a situation where b is 0. Here you notice here the thick line is on this point, so across time the value stays at 0, and here we are having that thick line at this point, so it stays the same at that point. 0, it's 0 all through. Now moving to the next one. Okay, there's another thing I would like to think. Okay, that's it, it stays at 0. All right, and in the case of this, in a situation whereby the value for b lies between -1 and 0, you have the b alternating signs. Now at this point, you see here it stays at this value up to a time period, a particular time period, then it now moves down again because this is negative. This point, below, this is 0, and now it assumes like a negative value. Then it moves up again, assuming a positive value, but not up to the initial point where it was. At this point, this, you will notice here that this is greater than this. So again, it goes down again to a negative value. So it keeps alternating signs. So something like that. The signs keep alternating. Then here again, it moves up. But now it's moving to a point that is not even up to where it was previously. So across time, when you see a value of b that is between a -1 and 0, it will keep alternating signs, and also it's divergent, not convergent. Let's put it that way. Now the next one is a situation whereby b is equal to -1. Yeah, in the case of this, what you notice is the signs keep alternating just like in the previous case here, but now uh, the function returns to its initial position. You notice here, okay, let's say here, starting from this point, this alternate signs, and then you move below the vertical line here, which is to a negative position. Now it stays at this point. Now when this thing is returning back here, it stays at that same length, at that same position as the initial point. But here again, it goes down again and then up, just like that, and it continues like that, moving away and away. But what we have here is that the thing keeps returning to that same position where it was before. So here, lastly here, we have b being less than -1. So here again, we have, okay, we have the sign oscillating here again. It keeps alternating between positive values and negative values. Here at this point, it moves down again, then up, then down, between +1 and -1, and then continues like that. Now again, it keeps moving further and further away. And another thing you notice here is that as it keeps alternating sign or oscillating, let's you were to use that technical word, here you notice that this keeps increasing. So here, alternating from here to here, by the time it alternates to a positive sign again, it is at a point where the value is greater than where it was before. And then when it alternates again, you notice here it goes even lesser than where it was before again. So by the time it's alternating to a positive sign again, it goes higher than where it was before. Just as a way of summarizing what we have explained so far, the graphs here. So here is a summary. Um, we have for this b, now the one of b greater than 1 is already explained here. We have explained the graph being explosive. Now it, it keeps moving further and further away from the point of equilibrium. So, and so, okay, now for the second case, which is b equals 1, the bt, the power of t is 1, so it stays the same as we move across time. That's just what this says. Then for this, bt decreases as t, that is as we move across time, the the function keeps decreasing and then keeps approaching 0. So here, minus for this other one here. Okay, for b equals 0, this stays the same as 0. So I've explained all of this before, so this is just a way of summarizing all we have said. So, and for the last one here, bt oscillates and move further and further away, like this here. It oscillates between positive and negative, and positive 1 and -1, and then it's not even positive and negative 1 because the height also keeps changing. So, and then it moves further and further away like that. All right, so I've come to the end of today's class, and again I would like to um, know if you have one or two questions to ask concerning this. Just feel free to drop those questions in the comment section below, and then in the next class we are going to be looking at the economic application of the concept of difference equation, how it can be applied to solve economic problems. All right, have a nice day. and bye for now.